everyone! Welcome back to my channel, Trash to Teach.
Optimizing Linux kernel settings for high-performance VR and gaming. You're in VR, you're mid-session. And then, stutter. That nauseating frame drop that pulls you right out of the experience. Or you're gaming, hitting 90 FPS on paper, but your system still feels like it's fighting you. Here's the thing nobody tells you. Your GPU isn't the problem. Your kernel is. The stock Ubuntu kernel is built to serve dozens of competing tasks fairly. Web browsers, background processes, a music player. That's great for a desktop. It is terrible for the brutal, unforgiving millisecond-level demands of real-time VR rendering. Today on Trash to Teach, we fix that. We're going to deploy the Zen Interactive tuning script, enable preempt_RT scheduling, lock the CPU governor to performance mode, and tune Hugepages, turning a standard Ubuntu install into a dedicated low-latency gaming and VR powerhouse. All of it free, all of it open source. Let's get into it. Why default kernels kill your frame rate. Let's talk about what's actually happening under the hood when you launch a VR game or a GPU-intensive title on stock Ubuntu. The default Linux scheduler, called CFS, the completely fair scheduler, was designed with fairness in mind. Every process gets a slice of CPU time in proportion to its priority. Sounds reasonable, right? The problem is that fair is the enemy of fast. VR doesn't want a fair share of the CPU. It wants the CPU right now, on demand, every 11 milliseconds, because that's your 90 Hz render deadline. When the scheduler lets a background process, say a package update check or a system monitor, preempt your render thread even briefly, you get a latency spike. That spike shows up as a micro-stutter. In flat games, it's annoying. In VR, it causes actual discomfort. There's also another culprit: interrupt coalescing and power-saving states. The kernel, by default, tries to be efficient. It batches interrupts, lets CPU cores idle into lower C states, and scales clock speeds down when load is light. These behaviors save power on a laptop, but they introduce unpredictable latency on a gaming or VR rig. And then there's memory. The default kernel uses 4 kilobyte memory pages. Modern games and VR engines allocate an access memory in massive chunks. All those tiny page lookups add overhead. We'll fix that with Hugepages later. So, unfair scheduler latency, power-saving interference, and tiny memory pages. 3 problems, 3 fixes. Let's start with the big one. Zen Interactive tuning and preempt _RT. Scheduling the Zen Interactive script is a community-maintained tuning collection that reconfigures dozens of kernel parameters in one shot. Things like scheduler latency targets, VM swappiness, IRQ affinity, and writeback settings. Think of it as an opinionated performance profile built specifically for interactive and gaming workloads. First, let's grab it and apply it. Open a terminal. I'll drop all commands in the description. Now for preempt_RT. By default, Ubuntu ships a preempt_voluntary kernel, meaning only certain safe preemption points exist. The RT patch changes the kernel so that almost every section of code can be preempted, including interrupt handlers. This dramatically reduces worst-case latency. On Ubuntu 24.04 and later, the RT kernel is available directly from the repos. No manual compilation needed. Check the Ubuntu low-latency or RT kernel packages. If you want full preempt_RT, check the Ubuntu mainline kernel PPA or your distro's RT packages. For most gaming and VR use cases, low latency gives you 90% of the benefit without potential hardware compatibility edge cases. I'll link resources for full RT in the description. After rebooting into the new kernel, your scheduler preemption model is already transformed, but we still have the CPU governor and memory to deal with. Locking the CPU governor to performance mode. Even with a tuned kernel, your CPU is still probably scaling its frequency dynamically. The PowerSave governor is the default on most systems. It lets the CPU clock down aggressively when it thinks load is low. The problem: games and VR engines have bursty, irregular loads. The CPU scales down between frames, then has to ramp back up, and that ramp up takes time you don't have. We switch to the performance governor, which pins the CPU at its maximum frequency. Yes, it uses more power. On a gaming rig, that's a trade you always want to make. To make this permanent, we add a system service that runs at boot. Create a small unit file. You can verify it worked with CPU power frequency-info. You should see your CPU locked at max frequency. On my test bench, switching governors alone gave a measurable reduction in 1% low frame times, those nasty outlier stutters that hit hardest in VR. Hugepages, eliminating memory bottlenecks. Let's talk memory. By default, the Linux kernel uses 4 kilobyte memory pages. Every time your game or VR engine needs to access memory, the CPU's memory management unit has to walk a translation table to map virtual addresses to physical ones. With 4 kilobyte pages, a 16 gigabyte game texture load requires millions of these lookups. The TLB, the translation look-aside buffer cache, can only hold so many entries. Miss the TLB and you take a penalty. Hugepages solve this by using 2 megabyte pages instead of 4 kilobytes. That's 512 times fewer TLB entries needed for the same memory footprint. For VR workloads that stream and access large texture atlases, this is a real measurable win. Linux supports 2 flavors: static Hugepages, reserved at boot, and transparent Hugepages, or THP. For gaming, THP with the MadVice policy is the sweet spot. It lets the kernel automatically promote memory regions that benefit from large pages without requiring app-level changes. For Proton and Wine-based games, there's one more trick: enabling Hugepages specifically for the game's memory allocations using wine_large_address_aware and dxvk_async. Steam's launch options make this straightforward. Combined with our scheduler and governor changes, Hugepages close the last major memory latency gap. At this point, your system is operating in a fundamentally different mode from a stock Ubuntu install. Benchmarks, bonus tweaks, and wrap-up. Let's look at real numbers. On my test bench, an older Ryzen 5 3600 with an RX 6700 XT, stock Ubuntu delivered average frame times of around 11.2 milliseconds at 1080p in a VR equivalent stress test, but with 1% lows hitting 18 to 22 milliseconds. After all 3 of today's changes, average frame time stayed roughly the same. You can't beat physics, but the 1% lows compressed down to 12 to 13 milliseconds. That's the stutter practically gone. For VR specifically, eliminating those 1% lows is everything. It's the difference between comfortable long sessions and motion sickness at the 30-minute mark. A few bonus tweaks I'll cover in the next video, but worth mentioning now. First, set your GPU to use the performance power profile in AMD GPU or NVIDIA settings, same principle as the CPU governor. Second, pin your game process to performance core CPU threads if you're on a hybrid architecture. Third, disable KSM, kernel same page merging. It scans memory for duplicates and introduces periodic latency spikes that wreck VR. That's the Trash2Teach kernel optimization stack. Zen Interactive tuning, preempt_RT scheduling, performance CPU governor, and Hugepages. 4 changes, all free, all reversible, and each one attacks a different layer of latency. If you came here from the Hyper-V and Ubuntu setup videos, this is the next level. Same hardware, dramatically better behavior. That's the whole ethos of this channel. You don't need to buy new gear, you need to know what to do with what you have. Drop your benchmark results in the comments. I want to see what kind of 1% low improvements you're getting on your rigs. If this helped, subscribe,